Okay, so welcome back to this next video in which we are discussing the Sylow Theorems. Okay, so we're currently on our way to proving the first Sylow theorem, and what we've so far proven is that the prime P does not divide the order of this set curly C. And remember, this set curly C is the set containing all subsets of our group of order P to the power of alpha. Okay, and we're going to use this fact that we've now successfully proven that this order of this set curly C is not a multiple of P to actually prove the first Sylow theorem, which is about the existence of Sylow P subgroups. Okay, right. So what's our next move then? Well, our next move is to establish a group action by our group capital G on this set curly C. Okay, so it's often a way of exploring a set, and we want to explore the set curly C here, and a way of often exploring sets is to create a group action by some group on that set. Okay, so a natural thing to now consider is let's create a group action by the group on curly C, and let's just see if it actually gives us any information about the set curly C. Okay, so we're going to create a group action by our group capital G on the set curly C, and remember, a group action consists of a group action composition table where we have all of the elements of the group being composed with all of the elements of the set. Okay, so what we'll do is we'll have all of the elements of the group over here, so all of the elements of the group will be given a row in our group action composition table, and I'll colour my group in red here. So here every element of the group is going to be given a row in my group action composition table, and now all of the elements of the set curly C, and remember the elements of this set curly C are actual subsets of the group capital G. Okay, all of the elements of the set curly C will be given a column in my group action composition table here. Okay, right. So how am I actually going to define this group action? How am I going to define little g, an element of the group, acting on a subset capital C of the set curly C? Again, just to make this crystal clear, let's say that this is the row in my group action composition table corresponding to little g, okay, and let's say that this is the column in my group action composition table corresponding to the subset capital C. So colour coding this in, here is little g, okay, and here is capital C in turquoise, and this then is going to be the answer in this little entry of the group action composition table. Okay, well, the way I'm going to define this is I'm going to define it to be the set GC, and when we write the element of the group next to this subset capital C, what this means is a new subset which will consist of all of the old elements of the original subset left multiplied by little g. So what you will do is you will multiply little c, which is an element of the original subset capital C, by the element little g in the group composition law. After all, this is a subset of elements of the group. Okay, so what you're going to do quite simply is you're going to take all of these elements of the group and you're going to left multiply them by the element little g. Now you might be tempted to say, well, that's just a left coset, but remember, this is just a subset capital C, it's not necessarily a subgroup. Okay, so that's why we're not calling it a left coset, because a left coset refers to doing this for a subgroup, okay, whereas we're just doing it for a subset. Okay, so what we'll end up with here is another subset of the group capital G, which has the same order as capital C. Okay, so it will also have order P to the power of alpha, and the reason it will have the same order as capital C is because we are going through all of the elements of capital C and left multiplying them by this element little g, and all of the answers we get will be distinct answers in the set, because if you think about it, what we're doing here, they will be distinct answers within the group, because if you think about it, what we're doing here, if this is the group composition table here, okay, so this is the group composition table rather than the group action composition table, and this is the row in the group composition table corresponding to little g, what you're doing is you're going through the elements of this subset capital C, and let's say all of this portion here let's say all of the columns in this portion are elements of the subset capital C here. Okay, so I'll colour it in green here. Okay, what we're doing then is we're multiplying all of these elements of the subset capital C by little g on the left, and effectively we're looking at this sub-portion of the row corresponding to little g here. That's going to be our new set that we're creating here. Okay, and we know that all of the rows of a group composition table, and indeed all of the columns of the group composition table, contain every element of the group once and only once. So when we go through the subset capital C and left multiply all the entries of this subset by little g, we'll end up with different answers in each case. So we'll end up with this subset having the same number of elements as capital C, i.e. it will be another subset of order p to the power of alpha, i.e. another element of curly C, which is good because this is going to be a group action by G on the set curly C. Okay, so the answers in this group action composition table should be back within the set curly C. So we've seen that yes, indeed they are. Okay, however, we need to make sure that this group action is going to actually obey the other two axioms of being a group action. Okay, we've made sure now that all the entries are actually going to be elements of the set back again. What we now need to do is make sure it does actually obey the axioms of being a group action. Okay, so let's firstly do axiom number 1 here. So axiom number 1 of a group action says that for all little g1 and little g2 that you can pick from the group, okay, so pick any two elements of the group, and for all subsets you can pick from our set curly C, okay, so whatever element you pick from the set curly C, it must be the case, okay, it must be the case that g1 acting on g2 acting on C, okay, so g1.g2.c must be the same as g1 composed with g2.c. Okay, so the group action composition law must be consistent with the group composition law. Okay, so this is our condition. This is axiom number 1 of a group action. Okay, right, so let's make sure that this is true. So let's just apply the very definition of what it means for an element of the group to act on a subset C. Okay, so g2.c, g2 acting on C, what does that mean? That means take the set g2c. So left multiply all of the elements of this subset C by g2. Okay, and we'll get a new subset of the same order, which is p to the power of alpha. Then what we want to do is act g1 on this answer, which is g2c. Okay, so what we'll now do is we'll take all of the entries in this subset and we'll left multiply them by g1. Okay, like so. Okay, so the set that we'll overall end up with will look like this. Okay, g1 of g2 little c, where little c is an element of capital C. Okay, so we've firstly left multiplied all the elements by g2, and then we've left multiplied all of those elements by g1. Okay, so this is our overall answer here. So that's the left hand side. Now let's explore further the right hand side here. So if we do the right hand side, what we're going to do is firstly compose g1 and g2 together in the group composition table, get the answer which is g1 composed with g2, and act this on capital C. Okay, so we're going to left multiply all of the elements of capital C by g1 composed with g2. So this is going to be g1, g2, C. Okay, so this is going to be the subset containing all things of the form g1 composed with g2 composed with C, where C is an element of capital C. Okay, and hopefully you can appreciate now that those two things are going to be absolutely equal to one another, because all of these compositions here, these two compositions, the composition between G1 and G2 and the composition between G2 and C, these are compositions in the group composition table, and the group composition law obeys associativity. Okay, so this thing here, G1 composed with G2 composed with C, is the same as G1 composed with G2, and then compose the answer with C, like so. Okay, so for absolutely all C, these two things are equal to one another. This argument holds true no matter what G1 or G2 or subset capital C that you actually pick. Okay, so axiom number 1 of a group action is indeed satisfied. Okay, now let's make sure of axiom number 2, so I'll just get a new piece of paper to do this. Okay, so let's now check axiom number 2 of group actions. And remember, axiom number 2 of group actions relates to the identity element. It says that the identity in the group must act on any subset to give back that same subset, and that must be true for all subsets that you take from the set curly C. Okay, so the identity must act on any element of the set curly C to give it that element back again. Okay, now why is that going to be true? Because when the identity acts on curly C, what that means is left multiply all the elements of the subset capital C by the identity. Okay, and I'm sorry if I said curly C, capital C here. When the identity acts on capital C, that means left multiply all the elements of this subset capital C by the identity. When you do that, of course, none of the elements are changed, so indeed you get capital C back again, and that is true for an arbitrary subset capital C from the set curly C. Okay, so we now have axiom number 2 of group actions being obeyed. Okay, right, so what that means is that indeed we do have a group action here of our group on this set curly C. Okay, so that means that what we can imagine is that all of the elements of the group can be associated with set permutations of curly C, and that the composition of these set permutations will be consistent with the composition law on the group. Okay, but actually what's more interesting for us, because we want to study curly C, is that we can partition up the set curly C into the orbits of this group action. So that's something you can always do. If you've got a group action by a group G on a set capital A, it allows you to partition the set capital A up into orbits. Again, this is often one of the ways that you can study a set by having a group acting on it. Okay, indeed, this is going to be very helpful for curly C. Okay, right, so let's draw a picture of this then. So we'll have our set curly C here. Okay, so this is the set of all subsets of the group of order p to the power of alpha. Okay, so I'll colour it in here in turquoise. And what we can now do is use the group action to partition up this set into subsets, basically. Okay, into the orbits specifically. And these won't necessarily all be the same size, so I'll draw it nice and interesting like so. Okay, so we split our set curly C into a well-defined partition, and I'll stress this is a well-defined partition. And let me just remind you of the definition of an orbit. So if we, for instance, take this orbit here, which I'll highlight in green here, and let's say this orbit might contain a subset which again I'll call capital C, it's just an arbitrary subset within curly C. Okay, then the definition of the orbit containing the element capital C is going to be all of the subsets in curly C that you can get by having elements of the group acting on capital C, basically. Okay, so it's going to be all things of the form little g acting on capital C, where little g is an element of the group. Okay, so you go through absolutely all of the elements of the group, you act them on the subset capital C, and you get answers, basically. You get other subsets within curly C, you stick them all into this subset here, and that's what we mean by the orbit of capital C. Okay? And we know, of course, that if we take any other element within the orbit of capital C and generate its orbit, you'll get the same answer. Okay, that's true for an arbitrary orbit of a set using group actions. Okay, right. So, why is this useful? Why is this going to be powerful? Okay, well, the reason this is going to be powerful is that we can use the orbits to write an equation for the order of C. Okay, so we're all about the order of C. Remember, we spent ages proving that the prime P does not divide the order C. Okay, so we're now coming back to the order of this curly C set. Okay, so the order of the set curly C is going to be the sum of the orders of all the orbits. Okay, and I'll just put capital O there. So you take the order of every single one of these orbits, add them all up. Okay, so your sum over all the orbits, and of course that will add up to the order of curly C. Okay, now here's where we're finally going to use the fact that we proved earlier. Okay, so the fact that we proved earlier said that the prime P did not divide the order of curly C. Okay, so curly C, whatever it is, if you take its prime factorization, it does not contain the prime P once. Okay, so no power of P appears in that. It is not a multiple of P. Okay, now what does that mean about the orbits? Well, that means that there must exist an orbit, and we might as well say that it's this orbit of the subset capital C, because after all, capital C was arbitrary. Okay, so there must exist an orbit, let's call it the orbit of capital C here, the subset capital C, such that the order of the orbit of capital C is not a multiple of P. So P does not divide, and I have to squash that in because I forgot to leave the space for it. Okay, there must exist an orbit such that P does not divide the order of that orbit. Now, why is that the case? Well, if all of the orders of all of the orbits divided P, okay, I've got that the wrong way around. If they were all multiples of P, if P divided all of them, okay, then that would mean they were all multiples of P. So in their prime factorizations, they all had some power of P. Okay, well that would mean that in this great big sum you could pull out that entire P, okay, and it would mean that the overall order of the set curly C would have to be a multiple of P. Okay, so if all of the orbits were multiples of P, when you add them all together you get another multiple of P. When you add loads of numbers which are all multiples of P together, you get another number which is a multiple of P. Okay, so because this is not a multiple of P, it must be the case that at least one of the orbits is not a multiple of P. Okay, I'm saying take that orbit, let's say arbitrarily that it's the orbit containing a subset which we'll call capital C. Okay, so we've now got this orbit of this subset capital C, okay, which is not a multiple of P. Okay, now how are we going to use that to construct a Sylow P subgroup? Okay, well now what we're going to do is apply the orbit stabilizer theorem. So I said we were going to use group actions, and indeed we are. We're going to use all of the theory that we developed of group actions. Okay, so remember the orbit stabilizer theorem says that the orbit of an element of our set, and remember the element of our set is curly C here, is going to be equal to the number of left cosets of the stabilizer of C in the group capital G. Okay, in the group capital G, which is called the index of the stabilizer of capital C in G in G. Okay, so remember the elements of the orbits can be put in bijective correspondence with the left cosets of the stabilizer, basically. Okay, right. So let me just remind you of the definition of the stabilizer. So the stabilizer of a subset, capital C, is a subgroup of capital G. It's always a subgroup, no matter what group action you're talking about. Okay? And the definition of it in this case, or actually I'll start with the arbitrary definition and then we'll apply our specific group action to interpret it. Okay, so the definition of a stabilizer of an element of the set on which the group is acting in the group G is all of the elements of the group, so all little g is an element of the group, capital G, such that when G acts on this element, which in this case is this subset capital C, it must give the same thing back again, so it must be capital C. So it's all of the elements of the group that have no effect on the subset capital C. Okay, so this is the definition of the stabilizer of C in G. Okay, now applying the actual definition of what it means for an element of the group to actually act on this subset capital C, we get that this is all little g which is an element of capital G, such that when you take all of the elements of capital C and left multiply them by little g, you get the subset back again. Now what that means is that when I compose an arbitrary element of the subset little c, so watch it, I've reduced now to little c, so this is an element of the subset. So when I compose little c with this little g from my group, okay, I must get some other element of the subset capital C back again, and that must be true for all little c is an element of capital C. So this is identical to this, basically. I'm saying that whenever I multiply some element of the subset capital C by little g on the left, it must be an element back in the subset capital C. That's the equivalent of saying that when I act little g on capital C, I get capital C back again. Okay, right, so that's the condition then for an element of the group to be within the stabilizer of this subset capital C. Okay, right, so the orbit stabilizer theorem then says that the number of elements in the orbit of capital C must be equal to the number of left cosets of this stabilizer of C and G in the group G. Okay, now because we're working with a finite group, because capital G is a finite group, we can find a nice expression for the index of the stabilizer of C in G in G. Okay, so I'm going to get a new expression for this, and the way it's going to work is just by looking at this picture. We can work this out just by looking at the picture. Okay, so here is the group, capital G, here. Okay, so here's our group, capital G. And then we'll have the stabilizer of C in G as a subgroup of our group capital G. So here it is. It's a bit big, but never mind. Okay, so here is our stabilizer of C in G. Okay, and what we are then doing is we're using the stabilizer of C in G to partition up our group into, let's say, left cosets. Okay, so we partition it up into left cosets, and this number, the index of the stabilizer of C in G means the number of left cosets you will end up with. Okay, but the size of all of these left cosets is the same as the size of the stabilizer of C and G. That's true for any arbitrary subgroup, that the size of the left or right cosets will be the same as the size of the subgroup. Okay, so what would happen if I multiplied this by the size of the stabilizer of C and G? Okay, well, I'd now be saying, okay, take the size of the subgroup here and multiply it by the number of left cosets, okay, which all have the same size as it. Well, I'd end up quite simply with the order of the group. Okay, the order of the group is just the size of this subgroup times how many left cosets it has, because eventually they will completely cover the group. Okay, and that then tells us that the index of the stabilizer of C in G in the group capital G is just equal to the order of the group divided by the order of the stabilizer of C in G. Okay, now this equation only applies for finite group theory. If the group capital G is an infinite group, then obviously you have a problem actually putting numbers on the orders. Okay, but if we're working in finite group theory, then we can apply this equation to the orbit stabilizer theorem and change the orbit stabilizer theorem into this form. So the order of the orbit of this subset C is going to be the same as the order of the group divided by the order of the stabilizer of C and G, or even better, we can rewrite this as the order of the orbit of C times the order of the stabilizer of C and G is equal to the order of the group. Now, some people actually quote the orbit stabilizer theorem in this form, but really this form only applies for finite group theory, whereas this form of the orbit stabilizer theorem would apply for infinite group theory, okay, which is why I usually quote it in this form. But this form is more important for us here because we're working with finite groups, and this is nicer because it gives us things that we actually have a meaning for, whereas this is a little bit more complicated. Okay, right, so what we're now going to do is use this equation to find our Sylow P subgroup. Okay, so what this is actually saying is that the order of the orbit of C, and remember we picked this orbit of C very specially because it was the orbit that was not a multiple of P. It was one of the orbits that was not a multiple of P. Okay, so we picked it very carefully and we proved that such an orbit must exist. Okay, then we've got the fact just from the orbit stabilizer theorem, which always applies for any orbit you like, that this times the stabilizer of C in G is equal to the order of the group. Now what I can do is replace the order of the group with p to the power of alpha times m, because I know what that is equal to, and then I get the fact that the order of the orbit of this element C, this subset C, times the order of the stabilizer of C in G is equal to p to the power of alpha times m. And let me just get this in full view. Okay, so this now is extremely important. Okay, what do we know about the order of the orbit C? We know that there is no power of p in its prime factorization. We know that p does not divide the order of the orbit of C. Okay, So there's no power of p in its prime factorisation. So where does this power of p here have to come from? It must have to come completely from the order of the stabiliser of C in G. Okay, and here's my claim now, that that stabiliser of C in G is actually your Sylow P subgroup. I have just managed to construct you a Sylow P subgroup, but I have not yet quite finished proving that. Okay, what I now know is that this must contain the complete p to the power of alpha, but there's a little droop here. I don't know that it doesn't contain some of this m. This m, remember, was the bit of the prime factorisation of the order of the group that was left over. Okay, I don't know that it doesn't contain a portion of this, which I'll call m bar, which might be a portion of this, and then the order of the orbit of C contains the rest. All I know is it has to contain the p to the alpha because there's no power of p in the order of the orbit of C. Okay, what I now need to show is that this m bar is 1, basically. It doesn't contain any of this m bit, it is just p to the power of alpha, and then I will have done. Okay, so how can I do that final line then, proving that this is just p to the power of alpha? Okay, well the way that I do it now is remembering what the definition of this special subgroup actually is, because this isn't just any old subgroup of the group capital G. This is the stabiliser of this subset capital C in G. Okay, so let me draw you a picture and then we can go with this. Okay, so here is our group capital G. Okay, and actually I should stick to the same colours that I have in the picture above. Okay, so here is my group capital G, and then I'll draw my stabiliser of C and G back on, and I'll draw it a more reasonable size this time. So here is my stabiliser of C and G. Okay, now remember that this thing, C, what actually was that? That was a subset of my group capital G, so let's just stick that on. It wasn't necessarily a subgroup, but it was a subset. Okay, so here is this subset capital C, and it was a special subset. It had something special about it, and the special thing about it was that it was an element of curly C, so its order was p to the power of alpha. Okay, now this is how I'm going to prove the final thing that I need to prove here. Okay, I'm going to take some arbitrary element of this subset capital C here, some arbitrary little x, which is an element of this subset capital C. And by the way, I've implied through this picture that capital C doesn't have any intersection with the stabiliser of C and G. That's, don't take that literally. Capital C is just some subset of capital G. And in fact, I might rectify that. I might extend it out to there. Okay, it just makes the picture look messier now, but it's just some subset. We don't know anything about capital C at the moment. Okay, it's just some subset, okay, of order p to the power of alpha. Okay, so you now take some little x from this subset capital C, and what you're going to do is you're going to use that little x to generate the right coset of the stabiliser of C in G under the element little x. So what you're now going to do is construct the right coset of the stabiliser of C in G under this element little x. Okay, so little x is some element of the subset capital C. Okay, and what I'm now going to do is construct the right coset of the stabiliser of C in G under little x. This is just a subgroup, and I'm now going to right multiply all of the elements of this subgroup by little x. So what I'm going to do is I'm going to go through all of the elements of the subgroup and right multiply them by little x. Okay, so I'll vary little g over all the elements of the stabiliser of C in G. But why is that a clever thing to do? Okay, well the reason that's a clever thing to do is we have to remember what the definition of the stabiliser of C in G was. Okay, remember all the elements in the stabiliser of C in G, they would left multiply any element of the subset capital C to give back another element of the subset capital C. Here is little x, okay, it's an element of capital C. So all of these answers that we get here, and they will all be distinct answers, so different elements of the stabiliser of C and G will give different answers, because effectively in the group composition table we are looking at the column corresponding to little x, and we know that that must contain all elements of the group once and only once. So these will all be distinct answers, okay, but they'll all be answers back in this subset capital C. Okay, so this will be completely contained within capital C. On the other hand, what do we know about the order of a right coset of the stabilizer of C in G under X? Well, we know that it will have the same order as the order of the stabilizer of C in G. When you take a right coset of a subgroup, it will have the same order as the original subgroup. Okay, so this set has order equal to the order of the stabilizer of C in G. Okay, but this is a subset of capital C, so its order must be less than or equal to the order of capital C. Okay, so what we know is that the order of the stabilizer of C and G is the same as the order of this right coset of the stabilizer of C and G under the element little x, but we know that this must be less than or equal to the order of this subset C, okay, because it's completely contained within the subset C, and we know that the order of the subset capital C is equal to p to the power of alpha. So now we can say that this is less than or equal to this. So the order of the stabilizer of C in G is less than or equal to p to the power of alpha. Combine this fact with this fact, and we get the fact that the order of the stabilizer of C in G must be equal to p to the power of alpha. Okay, and there you go. I have now found you the Sylow P subgroup. This stabilizer of this subset capital C in the group G is your Sylow P subgroup. Okay, so this proof is actually very nice because it's constructive. It tells you how to actually construct a Sylow P subgroup. Okay, what you have to do is you have to construct that set curly C, then create this group action of the group on the set curly C, use that to partition up the set curly C into these distinct orbits, which you could do, okay, then find one of these orbits which has order that is not a multiple of p, okay, and we've proven that you can always find such an orbit that cannot have p appearing in its prime factorization, okay, because of the fact that the order of curly C wasn't a multiple of p, okay. And then what you can do is you can construct the stabilizer of the subset C, where the subset C is one of the subsets within this orbit. Okay, so you construct the stabilizer of this subset C, which is one of the subsets within the orbit that is not a multiple of P, and that stabilizer of C in G, we have now proven that that will actually be a Sylow P subgroup. Okay, right. So we'll have a break there, and in the next video what we'll do is move on to the second Sylow theorem.